Hey everybody. So I want to start off and preface this video by talking about a subject that I've thought a lot about personally, but I think a lot of people generally don't think about very often, which is that like 3/4 of academia, or at least a large portion of academia, is generally traceable to one person, which is Aristotle. And then from there, it's essentially three people from there, right? Because there's the like Aristotelian lineage of Aristotle, Plato, and Socrates. So those three, but it's Aristotle, right? Like if you want to learn about communication, you start with Aristotle. If you want to learn about philosophy, you start with Aristotle. If you want to learn about psychology, you start with Aristotle. And then it's like all of like if you want to learn about ethics, you start with Aristotle, right? And it's just like all of these branches, they all start there. And to me, that's always been I don't know, like a big gap within that, right? Because it's like I don't know, it's just um, too narrow, right? And I've thought about that for a long time. And then like the reason why it is so like during that time there were a lot of competing schools, right? So like there's it was definitively like a lineage, right? Like it was a school, like the Aristotelian school, and then you have Plato and Socrates that are part of the Aristotelian school, but then you have other schools as well, right? Like Pythagoras, and like Diogenes, and like there's other schools, but it's just that like less is known about those other schools overall because of the fire of the Library of Alexandria. And then if that didn't happen, then a lot of history, a lot of like education overall would be like different, right? Because there'd be more branches of it, like not just like one singular branch, but like that one singular branch is just the it's easy for humans, like for human history to teach overall like one branch as opposed to like here's all the branches that actually exist, right? And then that happens in a lot of things, in a lot of ways, in a lot of areas. And then computation, computers, AI is where I'm getting at, and uh, driving towards within this, right? And then so at this point, like I've gone over kind of like the history of modern AI at this point, kind of repeatedly, right? It starts in the 1950s, and then it gets disproven mathematically with the Minsky paper, and the 1960s, which creates the like first like AI winter, and then from there it gets picked up in the 1980s by like small handful of people, like two, three people, and carried forward in the 1980s. And then you get stochastic gradient descent and backpropagation, like the two modern backbones of modern AI, if you will, that overcome those mathematical limitations that Minsky points out and references in the 1960s. So then AI picks up again, and then moves forward, but then it falters and then fails again. And then so you have the second AI winter that lasts until like the mid 2000s, and then GPUs come out, and GPUs actually end up being very beneficial for AI overall, and then ChatGPT, and then the rest is history, right? And that's kind of the progression and the outline of those things. And again, it's a very linear progression and a very narrow progression, especially in the 1980s period, right? Where it's just like so few, like it's like three people overall. And then, but in that period, like that 60s to 80s period, there are other alternatives to the overall core of the multi-layer perceptron and the perceptron that come out within these things, right? And the big thing with the problem that ends up being with the perceptron is that it ends up being not how the brain actually operates, right? And this becomes more common knowledge as we move forward from the 1950s, and then especially in the 1970s. There's a lot of exploration overall with regards towards like how the brain works, etc. And then during that period, there's an architecture that comes out called art, which we're going to explore deeply and heavily within today's video. That it comes up as an alternative to like multi-layer perceptrons at that time, and that lineage that is like far more functional than multi-layer perceptrons, doesn't rely on backpropagation, stochastic gradient descent, etc. This is all coming about and invented before that period, right? And then so, and it's a completely different, unique form, and it doesn't fall into the same problems as transformers architectures. And then the bottom line within it is it's um, allows for real-time learning, like something the aspect that transformers will never have. Right? Like there's the reason why transformers architecture has all these critics, like all of the critics of it, like, and more, especially like within like the AI research community, right, is because of that aspect of it. Once you realize that there are fundamental limitations within the architecture itself that prevent real-time learning, like the like actual real-time learning, like a human would, and you literally cannot do it mathematically with transformers, then you realize that there's that's a limitation, and you need to go and look at somewhere else, right? And that's where everyone is trying to go and explore, and then but everyone is it doesn't realize that the architecture in the 1970s exists that answered and solved that same exact problem. So let's go over it, right? So adaptive resonance theory, or ART, is one of the most important yet strangely underdiscussed families of neural architectures in all of machine learning. Long before deep learning, before transformers, before GPUs, ART tackled problems that modern architectures struggle with today: stability, continual learning, and the ability to incorporate new information without forgetting what was already known. While today's neural networks thrive on massive datasets and static training cycles, ART was designed with a different goal: to learn in real time without catastrophic forgetting, and to remain stable even as new information pours in. This document gives a clear, simple overview of ART's history, value, and modern practicality, especially as interest grows in alternatives to the transformer paradigm. Starting off with a brief history of ART. The origins. ART was developed in the late 1970s and early 1980s by neuroscientist Stephen Grossberg and collaborators. Grossberg's core research question was simple but profound: how does the brain learn new information without overwriting old memories? So it all starts off and always goes back to this process of like, how does the brain work overall? And like this is like this question of like how does the brain work overall is the fundamental question of AI, and like putting it exactly at how it is, and how it's moved forward, and where we're at with it is that you have engineers like me, engineer me stupid, right? Like I don't know how the human brain works. All I can do is make guesses and then simplify the heck out of that into something where I can actually like engineer and manufacture it. And then that's how this gets driven forward. It has been driven forward since the 1950s. Like it's always starts with this question, right? Which is like, me as an engineer, not as like a doctor or psychologist or anything like that, like how do I think that the human brain works, and like how do I solve for that, and how can I put that into manufacturing terms? And then so most theories at the time assumed that learning required wiping or weakening prior knowledge, an idea that fell apart when compared to real biological memory. Grossberg proposed that the brain preserves stability through resonance between bottom up sensory input and top down expectations. This led to the first ART model in 1976, followed by more advanced variants such as ART1, which utilized binary inputs, Fuzzy ART, which was utilized continuous inputs, ARTMAP, which utilized supervised learning, and then fusion architectures like Fuzzy ARTMAP, Gaussian ARTMAP, etc. And then so key insights within this is that the central insight behind art is now called the stability plasticity dilemma. Plasticity is the ability to learn new information, and stability is the ability to retain what has already been learned. Traditional neural networks fail this dilemma. They're plastic, but they're rarely stable, whereas art's architecture was explicitly built to solve this, being both plastic and stable, as opposed to traditional neural networks. And then, so what makes art unique? Art is fundamentally different from backpropagation based models. And this is important. And again, just highlighting and mentioning this entire method is invented before backpropagation, before stochastic gradient descent, before any of the, we'll call them the sins of neural networks, right? Like what a lot of people have problems with within the current neural network architectures. And then so it learns online, not offline. Again, solving another one of those sins of traditional neural networks. Most modern neural networks train in large batch cycles and can't easily adapt to new data without retraining. Art learns one sample at a time in real time. And then just like you would, right, is like kind of how it works, and but just like faster in some instances. And it avoids catastrophic forgetting because learning only occurs during a resonant state. Art does not overwrite older memories. The vigilance mechanism ensures that new patterns either match an existing category and refine it, or form a new category if the match isn't good enough. And then it uses feedback and resonance. Art models contain two-way communication between layers. A category is only reinforced if top-down expectations match bottom-up input. Learning occurs under resonance, hence the name. And then so this is like how it gets around and utilizes back propagation in a different way, right? Like the argument is all around back propagation is always the brain and other methods utilize methods like this, which are kind of like back propagation, and then you get into debates like this, right? And then so this falls very clearly on the line of areas where it's not back propagation. It's very clearly two-way communication within that whole entire debate. And then it can self-regulate memory granularity. A single parameter vigilance, or V, controls how fine-grained the categories become. Low vigilance means that it's a broad and general categories, and high vigilance means that it's many or highly specific categories, like a switch. And this gives art a form of dynamic adaptability that deep neural networks lack. It's like this is like these switches are a lot of what I build into all of my sidecars. And I build out, I'm going to show you and give you an art sidecar, coincidentally, which has this switch and this regulator within it, right? And this like regulator is to me like a as clearly pointed out here, one of the biggest areas and aspects that transformers lack at the moment, but can be added on outside of this method overall, just highlighting that. And so it doesn't require back propagation. Art never computes gradients. It never performs backprop. Its update rule uses a simple fuzzy and operation and incremental weight adjustments. This makes it extremely fast, simple to implement, and able to run on low power hardware. And I'll show you the results here. I run it without GPU very quickly on a data set. We're going to like the data set that I utilize is a simple MNIST data set showcasing 97% accuracy, and it runs in like 8 seconds. Why art still matters today, despite being older than most researchers in AI, myself included, art solves problems that deep learning still struggles with, including continual learning. Transformers forget unless you retrain them entirely on or bolt on specialized memory mechanisms like we have here, but art was built for lifelong learning from the start. Real-time adaptation. In a world where models must adapt on the fly, art is one of the few architectures truly designed for streaming non-stationary data. Transparent categorization. art doesn't store knowledge in dense and tangled weights. It forms explicit, interpretable prototypes for each learned category. And that's a big thing within this is that art models are like more describable, right, and more interpretable overall into how exactly they're getting the outputs. So for industries like law, things like that, like where it's you need the models to have interpretable results. These models would be the area and the key area that I would be looking towards, like law, medical, etc. These are the areas and the models that I would invest in overall, highlighting that, right? And then low data requirements. Art can learn robust categories from very small data sets, sometimes from a single example. This is like something like the big criticism of neural networks, right? That neural networks can't do this overall, whereas with the art architecture, this is what they're built to do. And it's a natural fit for edge computing because art is light on compute, simple to update, stable under repeated training. It's well suited for low power and embedded systems. So like a lot of AI advancement currently in the status quo is just history repeating itself, right? People going back to the 90s and then pulling back and going through back and combing through all this research and experiments where like there weren't GPUs involved, and then like, oh, this actually checks out and is pretty cool. Like go back 20 years before that, and then you're gonna see even more cool stuff. So just highlighting that, and then art versus modern neural networks. Below is a simplified comparison to highlight art's advantages and trade-offs. The strengths: there's no catastrophic forgetting. It's online learning, fast and lightweight, interpretable prototype memory, and robust under noise and drift. The limitations are that it's not suited for raw sensory data like images, which require pre-processing. It tends to form many categories if vigilance is too high, which is like a problem that every model is going to struggle with, meaning that it can't solve every single problem if the horizon window is too large, which we know already now will exist for every model, and does not perform dense hierarchical feature extraction the way that CNNs or transformers do. Doesn't mean that it can't be done. It's just that it's not been experimented around and it doesn't perform it in the same way that a CNN or a transformer does. And also, too, again, just highlighting these models can be easily and showcasing here to you coupled with CNNs and or transformers as well. Again, and then here they're complementary, not competitive, right? Art is not a replacement for transformers. It's an alternative paradigm. In fact, art can be paired with modern models. Use CNN or transformer embeddings as inputs to art for stable symbolic clustering, exactly how you see like the mixed Mamba models now, right, where they're utilizing half transformer and then half Mamba architecture, those types of things. Use art as a memory layer on top of latent embeddings. Use art as a prototype-based interpretability layer. As far as practical use cases, art's been successfully used in adaptive control systems, medical signal classification. I think this is one, just medical and law are the two. Anomaly detection in real time, sensor fusion, speech and EEG classification, streaming data analysis, and predictive maintenance. And then within anything that's signal detection, right? So there's a lot of areas that I'm not as deeply familiar with as well, but just the two broadest ones overall. Highlighting law and medical, and in my opinion. And then its stability and online nature make it ideal for environments where conditions change over time. And then why art is becoming relevant again. In an era dominated by transformers, interest in art is resurging for several reasons. First is the need for continual learning. This problem, and it's again mathematically, transformers won't and can't do this, which is why you have a lot of criticism around transformers. The world is not static. Models must adapt to new data without retraining from scratch. The return of neuromorphic and biologically inspired computing. Art's design is closer to biological cortex than any gradient-based model. So again, you have the history of AI, right? You have the first AI winter because MLP models are proven to not, or before MLP models are like the prototype of the models are figured to not work mathematically overall with the whole entire debate over the perceptron, right? So perceptrons are found to not mathematically work, and then that leads to the AI winter, and then you have what ends up being a sharp diversion from the initial aspect of AI in the 1980s, where it deviates 100% and then it invokes stochastic gradient descent and backpropagation, which are seen nowhere in any sort of biological process. And then so it breaks away from this, which was like the initial goal and concept of AI, whereas art was like a continuation of that same lineage, right? And then so hybrid architectures are rising. Architectures like my Zarya architecture, or resonance-based systems, sidecars, and prototype memory networks fit naturally with art principles. Like it's like a lot of work that I see around resonance, including my own work, etc., are essentially within this same lineage and like kind of like cousins, like grandsons, etc., to this particular framework overall. And then so efficiency matters. As compute costs rise, efficient models become more attractive. Art is extremely efficient. So, as a summary, art is one of the most underrated yet powerful families of neural architectures. It was decades ahead of its time in addressing stability versus plasticity, continual learning, real time adaptation, interpretable category formation, biologically plausible computation. While it doesn't replace modern deep learning, it solves problems deep learning still cannot. Its principles can enrich modern architectures, serve as robust memory backbones, and provide stability in systems that must learn continually. For newcomers, art is a reminder that the future of AI may not belong solely to bigger models, but to smarter, more adaptive ones. And then so going into the code itself, I want to introduce you overall to the art sidecar at the end of this. But what the notebook contains is a full fuzzy art implementation utilizing NumPy, and then we'll train it on the. So I mentioned earlier that it was MNIST. It's actually Iris on the Iris dataset, and then the end result is giving you a production ready fuzzy arts sidecar utilizing PyTorch. And then so here's just kind of a full breakdown of this. You can go ahead and read through the full breakdown of the model here. But so here's the fuzzy art demo on the Iris dataset. And then so just kind of showcasing you, this is the full architecture of the model, including the training and the evaluation. And you can see this entire thing ran in 9 seconds, right? And then no GPU enabled. You don't have to enable GPU, just simple CPU. And you can see here, so it takes the Iris dataset, creates the shape of the data set, and then so this model's all zeros and ones, right? So that's the beautiful thing about these tables, is it's matrix tables, right? Like, so matrix arrays tables, but rather than like numbers between zero, like like your typical matrix tables with neural networks wouldn't look like this, right? They would either look like 0 point something, and there'd be numbers here. It's either 0 or 1. That's that's it. That's the entirety of the matrix table. So very simple on that end, right? And I love that, which is what makes it easy to run within this. And then so that creates categories, and then you can see here within that it creates clustering categories, right? And then so it creates in this its first go around, it creates 11 categories, and then it has 86% accuracy. And then the second go around, 21 categories at 91. 31 categories at 92, 44 at 96, and then 50 at 96. And then so you can see that the problem that you run into is that it starts to use more and more categories to increase the accuracy, which can over time increase the need for performance and GPU. But again, this was invented in the 1970s, so 30 years before GPU even came out. So none of these have ever been scaled up to anywhere near the same level as say ChatGPT, etc. Right? And then so these are the smallest of small models in comparison. And then so looking at that, here our end result though is 97% accuracy on the iris data set, right? Which is like that's not unheard of or anything spectacular, but it's again running in 9 seconds on CPU, and we can see here very clear, like it's very clear clustering. Clustering is its strong suit. Like this is like identical essentially. Like if you're looking at these two, they're kind of different colored, right? But it's identical, like straight up identical as to like where the pattern matching is occurring within this. Like this is all like flawless. Like it's awesome overall to see that. And then within this, like as showcased and as mentioned earlier, I want to give you a sidecar within this. So sidecar is a fuzzy art sidecar memory for arbitrary embeddings. And then so you can utilize this overall, no back propagation, and then so it allows for like that continuous inputs that we can and that like a continual learning that you can bolt on essentially to a transformer, and then utilize that overall, and then you would just essentially just utilize this code to bolt onto any like LLM model, etc., that you would want to utilize, and it's a full functioning and working sidecar. And then so here's all the code for that. And then so overall, hope you like art models overall. They're pretty cool. You should check them out. I'll leave a link to this Substack article so then you can also take a look at the code. And then if you like this type of content overall, please like and subscribe. Thank you very much.